So I know I have here, we're going to do linear regression tonight, but I'm going to start with from last week, and just give you guys an update on me. Recruiters presenting me at a couple places pretty soon. Levi's here in San Francisco, and Sephora, those two. So we'll see what happens. The Sephora job would actually be data scientist. So I'm hoping that that's the one. That's what I'm aiming for. But meanwhile, I'm also teaching another class in machine learning with Simplilearn. I mentioned it last time, and it's rough. The hours, 4 hours on Saturday and 4 hours on Sunday, from my time, 7 a.m. to 11 a.m. both days for 5 weeks straight. Just finished my third week, 2 more weeks to go. And it's rough. But it's machine learning, advanced machine learning. And it's much more statistical based stuff that I put together. So anyway. All right, so let's finish up from last week. Okay, this is, drag this down here, get it out of the way. Okay, so let me pull up where we were last week. Just give me a second here. Did not bring my second screen in, so all right. Last week we were finishing up neural networks, and we got to the second data set that I was going to run it on, the Iris data set, and ran out of time. For that, we did it on, just to review real quick, we did it on the XOR data set, really tiny data set. Smallest data set you'll probably ever use. I guess the only thing smaller would be maybe inversion. So the XOR data set is what we did last time. Let's do exactly what we did last time, but on a bigger data set, the Iris data set. Yeah, if you guys want to post questions, you can post it in the Q&A or right here in the chat. Either place is good. And please don't hesitate to stop me with questions and or comments. So what we did last time was very similar to this, but we're also pulling in from scikit-learn. We're importing data sets because our the Iris data set is standard. It comes with scikit-learn. Scikit-learn comes with several data sets, this being one of them. So this is how you do it. It just iris equals datasets.load iris, and then we're going to set x to iris.data and y to this. I know this is ugly. It's basically iris.dataset, but we're making it a two-dimensional data set, a two-dimensional matrix, and then flipping it, transposing it, so that it fits into our model. So hold on, I'm going to pull up and the GitHub for this. If you want to follow along, I posted it in the chat. So you can go pull that up. You scroll up in the chat. I'm not sure. Can somebody who was one of the later ones logging in, can you scroll up to earlier chat and see what I posted? I posted a couple of links to my GitHub. Okay, then I will paste them again. Thank you, Sachin. Your kindness is duly appreciated. All right. Not today. It's not appreciated today, or it didn't show up today. Kidding. All right. All right. Okay. So I'm posting two GitHubs, two spots on my GitHub. One is lecture 4 from the lecture series 2. Now, the other one is what we're going to go over tonight from scratch, the linear regression. I put all of that into lecture 5, but it's in the lecture series 1 from when I went through this the first time. I haven't created the GitHub for lecture 5 for series 2. That is to come, along with quite a bunch of other things, homework and quizzes and stuff like that. So I'll get it out there to you guys. I know you're really dying to do the homework and you know, be tested on the quizzes. Okay, so let me pull up. Right? Am I right? You guys really want the quizzes? Crickets. All right, there we go. Okay, so where were we here? Hold on, I had it up. Too many windows open. Okay, so I'm going to need to start over again. Might have lost it. Post links. I have not posted links to all of that yet. I have to create it. And I pass it over to Kyle, and Kyle posts it up. Right now, the video is up for last week. That should be out there if it's done processing. All right, so Dropbox, learning. Okay, so this is programs series 2 and no, lecture 4 and Iris dataset. Okay, so here we are. So these are the first couple of things that I already talked about. We're using NumPy, Matplotlib libraries, scikit-learn. We're pulling in the data sets. And this is, hold on. Yeah, I'm gonna have to do this once in a while because the lights are on the timer. Oh, hold on. Somehow, okay. I was also posting to just the panelists. There's the one for right now, and the next one Like I said, I wish it automatically set. Zoom is very, very, very good, and I like it much better than WebEx, which is what Simplilearn uses. Oh, so it just seems so antiquated. Okay. No problem, fun, everybody. Okay. So back to this. Okay, loaded in. Oh, yeah. You got. Let me just pause just for a second. Let you guys get the data sets up. Get the Jupyter notebooks up so you can follow along. Meanwhile, I'm going to pull up my favorite picture of deep learning. You guys have probably seen my website. Need to update it. I think the guys at Simplilearn looked at my website, saw the syllabus for this lecture, and created the class based on that. Because it's new. They created a class and said, "Yeah, you want to come teach us?" I said, "Okay, sure." I was bored. Okay. Hold on 1 second here. Let's go back. Oh, I know. Let me scroll down. Okay. This is my favorite picture right here. Deep learning. Since I do underwater rugby, which actually I do underwater hockey and I haven't done underwater rugby yet. That's this next weekend I'm going to try it. Just anything underwater is my favorite stuff to do. But this guy's definitely over his head in deep learning, and it doesn't take much to do deep learning. So the fact that it's over his head just means that I don't know, he hasn't gotten into AI or machine learning at all. Deep learning is, we're doing it now with just any neural network that's over just one neuron or one layer. If you go to 2 layers, you're doing deep learning. There's been a lot of advances and a lot of uses of it, more uses of it than advances. So yeah, it's not as bad as everybody makes it out to be. Okay. Okay, so all right, so continue on. I'm going to assume everybody's got their Jupyter notebooks up. And we went over this last time. We defined the sigmoid as a function, which is the sigmoid is if derivative equals false, we're passing in this what we're taking the sigmoid of, and then we're passing in whether we're going to return back the derivative of the sigmoid or just the sigmoid of x. If we're doing the derivative, we return this function, which is x times 1 minus x. If we're not doing the derivative, then we're just returning the sigmoid, which is 1 over 1 plus e to the minus x, or exponent of minus x. Okay, here's a feed-forward function where we're starting with x and returning AO and AH, but AO is the final output. AH is the output of the first layer, the hidden layer. H for hidden. Okay, Okay, and we're going to define some parameters of our learning. So one of the parameters is our learning rate, 0.01. In this program, we called it ETA. And that's how far we're moving for each step. We're calculating the gradient and then multiplying the gradient by 0.01. So we're moving a part of the gradient, a very small amount. We can increase it and move more of the gradient, but we might overshoot the minimum, overshoot the, we're moving down the gradient, down the curve, and trying to get to the bottom. But if we overshoot the lowest point, if the gradient's too big, then we'll have to go back the other way. So we'll oscillate if our learning rate is too large. Okay, so that's learning rate. It's a function of gradient descent, and I know this is all very complex. Gradient descent algorithm. It's like people try to learn neural networks. They get stuck with gradient descent. Well, that isn't just neural networks that do gradient descent. We're going to show shortly that linear regression and logistic regression, they both can be done with gradient descent, and most often are. It's more efficient to do gradient descent than it is just solve it. We're going to show why that is tonight. Okay, so so epochs. Epochs is the number of times we're going to go through our data. This is a gradient descent. This is an iterative approach to coming up with the answer. We're not just solving for the answer. We're moving a little bit toward the minimum error. And so how many times do we have to move to get there? Well, we're going to go through all of our data. We have 150 rows in this data. We're going to go through it 1,000 times, each time getting a little bit closer. The bigger our learning rate, the less times we have to go through our data. But we may not even get to our lowest point if our learning rate's too big. We'll actually diverge. We'll get worse each time. Okay, so we're going to go through our data 1,000 times. That's the number of epochs. And then also, let's define the number of hidden neurons. We're going to pick 10 hidden neurons. We've got 4 inputs, 1 output, and 10 hidden neurons. Didn't really show the data here, what the data looks like. Might be interesting to look at, but yeah, just 4 inputs and 100 rows, 4 inputs, and then 1 output, which is the outputs are what type of iris it is. A lot of you are familiar with the iris data set already. If you're not, definitely take a look at the data here and see what it looks like so you can become familiar with it. Okay, so the first thing that we're going to do is, just like we did last week, initialize all the weights to random numbers. So that's what these 2 functions. And how many weights are there? There's the number of hidden times the length of the input. That's the number of weights there are between the 0th layer and the first layer. That's the input and the hidden layer. And then we have another set of weights that's between the hidden layer and the output layer. And that's hidden times 1. That's the number of weights we end up with here. we can show actually what those look like. Let's do that. W01. Okay. We said we had how many inputs? Let's scroll down a little bit. These are set and done. With the chat in the way. Okay. So how many weights do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 by 1, 2, 3, 4. So we have 4 inputs times 10 hidden layers, hidden neurons in the hidden layer. So that would mean we have 40 weights, it's a 10 by 4 matrix. So let's look at the other matrix. It's the weight given to hidden to output layer. There's one output layer, there's 10, one output neuron, there's 10 neurons in the hidden layer. So therefore we have 10 weights, 1 per neuron. Okay. Now we're going to go through for each epoch, 1,000 epochs, we're going to go through all of our data and do the training. We went through this in detail last week. I'm not going to go through it in detail this week. Hopefully you guys watched the videos. If not, I would strongly suggest going back and watching last week's video. I explained all of this code in detail. So that would make it pretty evident. But since tonight, it's only supposed to be an hour, will probably be an hour and a half. I apologize. For those on the East Coast, that will put it pretty late. For India, that'll bring you to like 8:30 in the morning. So it shouldn't be too bad. All right, so something just different that I did here that I didn't do last time was split my error total up into 3 components. A component of each output type, each class. I'm going to call it class. So I've got a total error, and then I've got the part of the error that is attributed to the total error that is only for, like here, I set the error to one part of the total error, where the output is equal to 1 is one error, one amount of error, where the output is equal to 0 and the output is equal to 2. Those 0, 1, and 2 are represent the 3 different types of iris, 3 different classes of iris. So what I'm doing is I'm showing the error that is coming from, I forget the 3 different types of iris. Does anybody know what the different types of iris are? I remember one of them. See if anybody can pop that in. If anybody's already familiar with the iris data set. I know it takes a minute to type it. One is setosa. Okay. You guys should Google the iris data set. Sorry about the light in here. Okay, I'm in our training room. As you can see, I've got stuff on the board behind me. Virginica. So Setosa, Virginica, and what's the other one? Okay, there you go, Versicolor. All right, good. Himrus and Amit, very good. Okay, so okay, and we'll show this error when we're all done, what the error looks like as we train. So I'll go ahead and run it, or that's just no, that is actually doing it. Let's see if it's done already. Yeah, it went very quick. Okay. Okay, so now let's look at the error at the very end. Total error, we still have quite a bit of error, and this is the mean squared error. Actually, it's not the mean squared error, it's a total error. It's a total error. So it's just a sum squared error. So the type 0, it did fine on. The error now is very small. Type 1 is also very small. Type 2 is pretty big. It's 25. It's 1 per. So for some reason, this neural network didn't train very well. And that's going to be part of your homework to tell me why. So looking at what the error did, notice it changed when I plotted it the second time. It's because of randomization. It randomized and it converged more quickly this time than it did last time. But I'm showing the error over time here. I say over time for over the epochs. So it started off, the error was, total error is blue, was a total of 50. The error dropped, this one dropped. This one was already low from the randomization. It started out low, kind of went up and then went down again. This error did not, it went up and then dropped back down to 25. So that's pretty interesting. That's the one that's contributing to the final error. The other two errors, you know, went away. If I'd randomized differently, maybe better, then they all would have kind of started in the middle rather than this one starting at 1 or 25, this one starting at 25, and this one starting at 0. But that's a function of how the randomization that I did at the very beginning. Probably should have randomized somewhere around, so, you know, probably lower. I probably randomized between 0 and 1, and I needed to randomize a lot lower because I'm adding up all of those. And it's just, yeah, they got too big. So, all right, so here's here's the data, and then I have added on to the end what the final actual was. What the final predicted, I should say. The actual is 4, and then predicted is the last column. So I've got 4 inputs. These are the different measurements of the flowers. And then I've got a 0 column for this class. And then I say 0 because 0 is in the column for that class, 1's in the column for that class of iris, and 2's in the column for the last one. And then I've got my predicted outputs. You know, see for the 0 class, I've got, you know, pretty low numbers. For the 1 class, I've got numbers that are pretty close to 1. And then for my 2 class, I have also numbers pretty close to 1. So that right there should give you a hint as far as why that last one did not, why one of the classes didn't converge to an error of 0. Okay, so that's it for the iris. So back to the slides. Okay. Okay, so it should be lecture 4 homework, that's right. All right, so for homework, I have a bunch of different things here. I want you guys to try out on the neural networks. I went through neural networks twice and then once tonight. So this should make the homework easier. The lecture 4 and lecture 5 both were going through the neural networks. And then tonight I went through it for another 35 minutes. So what I want you to do is for the XOR graph the learning curve, and then try adjusting hyperparameters. The learning rate, the number of hidden layers, and number of hidden neurons. Hidden layers, that's going to be the most difficult part. The hidden neurons, that should be easy. Learning rate, that should be easy. But try adjusting those. And if you're really adventurous, then try adding other hyperparameters like momentum, dropout, stuff like that. This is, for these, it'd be fine if you want to, instead of using the neural network code I gave you, where you're actually doing the whole neural network by hand, you could use scikit-learn for this one if you want. That would be a lot easier. That and the hidden layers, doing it with scikit-learn, Keras. You can do it with TensorFlow if you want. I'd be very impressed. TensorFlow is almost like what I did, doing it by hand. As far as the number of steps, the amount of difficulty. But Keras would take care of it all for you, and scikit-learn would as well. This is more advanced. Create a fit function rather than the way I did it with just a loop. You'd put all of that inside of a fit function and instantiate a neural network. Just make this object oriented. And that would, this is how first of all, you create a fit function, then you could create a class and stick the fit function as a method of the class, and then a predict function, predict method inside the class, and then add hyperparameters, make it more complicated. Okay, so that's on the XOR, so the basic neural network model. And for the iris data set, a couple of things. What was the issue? That's one homework. And also expand this to not just train and then show the result of the training, do a split. Do training validation and test. So I said verification here, validation, and then test. And also for the homework, what's your motivation for in this class? Besides just getting a job. Okay, what is your passion in this area, in neural networks, deep learning, or in data science in general, statistics, statistical methods, analytics? What's your passion? What's your motivation? All right, so that's it. Okay, PyTorch. Yes, please do PyTorch instead of TensorFlow. If you're more familiar with that, or in general, I'm just not. I just can't seem to be excited about TensorFlow, especially since Keras. Everywhere I've seen TensorFlow, it's because it's part of Keras, and that's how they did it. Every time I've seen just TensorFlow by itself, seems to be just a mathematical exercise. So it's just, to me, not that useful. You have a 30-year, different, layer types inside Keras. You would need to know TensorFlow if you needed to create a 31st. So I'm just not too excited about TensorFlow. PyTorch is just much more straightforward. It's the same kind of thing, but it's more straightforward than TensorFlow. So, okay, right, it's more readable. So, I come to this with a certain bias, as everybody does. We should eliminate the bias, right? That's one of the goals we do as a data scientist, but it's just difficult. All right. Linear regression. That's next. I could change the time here too. Hold on. All right. So what we're going to do tonight, we're not going to go over quizzes. Sorry. Forgot to take this out. We did this. We went over the IRIS homework. Actually, okay, this is also from last time. Okay. So yeah, we reviewed some of the neural networks. What we're going to do now is talk about linear regression and do two different solutions for the linear regression problem as part of the and learning linear regression. It's good to know the theory of linear regression and logistic regression, especially if you're interested in deep learning, if you're interested in neural networks, because there's a lot of parallels, direct parallels. There's also some parallels in deep learning to some of the other statistical techniques, but it's more abstract. Here it's more direct, and we can show that, especially logistic regression. And logistic regression will be next time. As far as the two different ways to solve it, there's a direct solving the linear regression problem just through some mathematics, and then there's a gradient descent solution. So it's good practice to learn the basics of linear regression, logistic regression, practice for deep learning, for getting into that end of it. All right, so This is something we already went over, but it's just a good thing to throw up here as part of a review. You know, the different types of machine learning techniques. And we're doing supervised so far. We will do unsupervised. But even supervised can be broken into classification and regression. And supervised is where we've got an output that we're trying to predict. We're trying to train on, trying to learn. We know what we want. We are helping our data set, helping our model by telling it what we want it to come to. And usually you iterate to get there, but we're going to show tonight, not in every model do you have to iterate. You can just solve it. So, so within supervised, we got classification and regression, where classification is if your output that you're trying to train on can be put into groups, and then you're trying to learn which group your row of your data, your sample, fits into. That would be classification, like fraud or not fraud, cancerous or not cancerous. What we just did, XOR, the output is either 0 or 1. That's, two different classes. Also, we were classifying our irises as being, Setosa, Virginica, or the other one. I can never remember the three of them. Mental block. So that's what classification is. We're trying to predict either a type or a class, and the different algorithms that you would use for that. Logistic regression is the most basic. It's also usually the least accurate. It has the least potential of being, or the least potential of being the most accurate. K's nearest neighbors is another classification algorithm. Decision trees can be used as a classification. They can also be used as regression. Naive Bayes is a classification algorithm. And the support vector classifier is one type. And, it's basically, this is a support vector machine, okay? And you have different types of support vector machines. You have either using as a classifier or regression, which we'll get to regression in a second. And it can be, you can simplify the algorithm to be just linear. If it's nonlinear, you just don't put the word linear in front. Okay, so that was classification. Regression is when your output is a continuous variable. It's not a class. We're trying to predict a number, like a dollar amount, like a temperature. Those, like a distance. Those would be continuous variables, and when we predict that, it's called a regression algorithm. Or we use a regression algorithm to predict that kind of problem. So different types of regression algorithms. One is the linear regression, which we're going to go over tonight. Regression trees or decision trees, but if they're used for a regression problem, sometimes you call it a regression tree. Random forest is one of those types, but random forest can also be used for classification. A support vector regression, SVR, that's when you use a support vector machine to classify, or not to classify, to do the regression problem. And there's many more of both. These are all statistical methods. Neural networks would be, or deep learning would be beyond the statistical method. In there, we're actually mimicking the way the brain works. Okay, so that's more of a biological type of algorithm. Okay, so what we're going to do with linear regression tonight, first I'm going to kind of give a description, motivation of linear regression, what a problem looks like that we're going to do linear regression on, show you the data set. Then we're going to go through two different methodologies of doing the linear regression. A matrix solution, which is just solving your linear regression for the linear regression model. And we're going to give the mathematics behind it, the derivation, and then also show you the code, how you do it in Python. Then we're going to do also the same linear regression problem, but we're going to solve it a different way. We're going to solve it using gradient descent. And we're going to show all the math behind that gradient descent. It's not much. We've kind of already gone through it. With the neural network, it's very similar. And then we're going to implement that in Python. And then we'll do a little comparison to neural network as far as how we can see that they're similar. Okay. So what kind of data does linear regression work on? What kind of problem, what kind of use case would you use a linear regression to solve? A couple of them are like the salary versus years of experience. So if you're trying to predict the salary, your salary based upon years of experience, your salary is a continuous number. It's not a class. And you're trying to do it based on some parameter and/or parameters. In this case, it's just one parameter. And if you graphed it, it would look like this. You could imagine a line going through this being a continuous line. So that's a regression problem. Your output is a continuous variable. So the answer, what we're trying to solve for in a linear regression, we're trying to come up with a way to represent that line that best fits all of that data. And when I say line, okay, I don't mean curve, okay, I mean line, okay, because this is linear regression. We're assuming that the form of this data, form of the best fit to the data is a line. And how do you represent a line in math, in an equation? It's y equals mx plus b, where b is the slope, or where the line crosses the y-axis, and m is the slope of that line. How far it's rise over run. So you go up 2 over 1, so it's a -2. Slope is -2. Okay, this is basic, geometry back to 6th grade, I think it was. Maybe later, maybe 8th grade. Anyway, so if your data was perfect, a perfect line, then that would be the form. But we're dealing with real world data, okay, and we're going to try to come up with an approximation of the data and predict, see if we can come up with a solution to the data that if we haven't seen an input, haven't seen a particular data set or a particular sample, then we'd be able to accurately predict what the outcome would be. So this is what our data would really look like in real life. It's never a perfect straight line. So we're going to come up with a approximation, a line that is an approximation of that data. And the way we're writing that line is, again, y equals mx plus b, then plus this e term, okay, error term. And that varies on each point. Okay, so with that said, okay, that's our actual function. We can rewrite that. Okay, and then what we're doing at this point is we're going to solve for m and b. We want to know what that m and b are. So we're going to do a little math here to solve for that. So once we write this, we can rewrite y equals mx plus b plus e as this, where y is the vector equals xa plus e, where x is rewritten as put a bunch of ones in the first column, and then x1 through xn, where that's each one of your elements of your data set, each row of your data set, the x part. Because remember, we've got a bunch of x's here. It's a vector. So rewrite, x is this, and then y, to line that up, it's your data set, but your output, okay? And then we're going to write a as b and m. B, the first part of that vector, m is the second. And e is all of the errors, e1 through en, okay? Each one of these little distances here. So you can see from matrix multiplication, from basic linear algebra, that we just, rewrote that. Okay, something, a question maybe? Okay, explain B again. Okay, B is, if we look at the line, B is the y-intercept. Y equals m, where m is the slope of this line and b is the y-intercept. In this case, b is 14. So, so that's it. M being the slope. Okay, the error is the error of each point. Okay, so how do you solve this? For what we're trying to come up with is A, right? B and M is what we're trying to come up with. So if we could somehow solve this for A, then we're good. Now we're going to assume something. We're going to assume that the sum of all these errors is 0. What happens if we assume that? Let's think about that for a second. We have some errors that are above, some errors that are below, some errors that are above, some errors that are below. Okay, imagine the line being not exactly the best fit for all of these. Then in that case, the sum of the errors would not be 0. I have to figure out how to fix that if I'm going to continue doing it in this room. So basically, if this is the best fit, we can show that the sum of all those errors is 0. So we're just going to make that assumption that we picked the best line. And if we make that assumption, then the answer to this ends up being the best line. When we solve for A, we can just cross off E. That will make it so that indeed we have the best line. So how would you solve this? Well, this is the way. You don't just divide both sides by x, y over x. If it was one dimension, yes, that would work. If we only had one value, one row in our data set, one sample, then yeah, dividing it would work. But we've got matrices. So the way you do that in linear algebra, you just memorize this. Take x, okay, you do x transpose, you multiply it by itself, you take the inverse, okay, we talked about inverse in a previous class, how you take the inverse of a matrix. Because when you do this multiplication, you end up with I think a 2x2 matrix. So when you take the inverse, you just end up with that inverse. And then you multiply by x transpose. Take x, transpose it, and then you multiply the two. And what you end up with, then you multiply that by your y, your output. And what you end up with is A. Then you have your B and your M. Simple math. Simple, the basic, this is some basic linear algebra. If you just know this function, then this formula, then you could just plug in all your data set and come up with A. Now, some quick intuition about this. Why would we learn any other way to do it if we had the final answer this way? The reason is because if we have, this is just if we have one variable on the input, at 1x. I know we have x1 through xn here, but that's rows of our data set. But let's say we had several features, x1, x11, x1, okay, got to get our subscripts right here. Let's say instead of x, we called it A, so it'd be A1, A2, A3 going down, and then B would be another input, C would be another input, another column of this matrix, okay? We end up with something pretty big to do an inverse of. That inverse is very computationally intensive. Inverse of a matrix, if it's not just a 2x2 matrix, will take quite a while if it's 10 by 10. And sometimes you won't have an inverse. Sometimes you'll have singularity, where you won't have a best fit line for all these data points. Like for instance, let's say that all these points were on top of each other vertically. then you won't have a line that gives, then the line you come up with would be a vertical line, which that would be the slope is infinity. So that would be a problem with this approach. You would be dividing by 0. That's what will happen. So there's some problems with this approach. So a better approach would be gradient descent. You'll come up with an answer. It may not be the best answer, but at least you'll have an answer. You won't have a singularity where you just can't come up with an answer. Okay, so let's pull up the GitHub that I shared. I haven't pushed this out to the Series 2 GitHub yet. It's still in the Series 1, but it's lecture 5 of the Series 1 out on my GitHub. So, solving using linear algebra. Okay. So everybody up with me so far? Hopefully you guys are following along on your laptop, on your machine. It's super important to be able to do this. I can't impress how important it is to be able to run a notebook running along just with me. If you have any problems with that, definitely ping me, ping the group. You know, just you got to be able to do this kind of programming, you know, on your own to do projects, to do good projects for data science, for machine learning, and it's not too hard, especially to follow along with what I'm doing, because I'm giving you everything. Okay, so all right, we're bringing in our libraries. We're gonna bring in NumPy. I'm gonna also bring in an array, and from within NumPy, I'm gonna bring in linear algebra inverse, the INV, and also I'm gonna plot a little bit here. So I'm gonna import pyplot. All right, so I'm gonna set up my data. I'm just going to set the data here. I'm not going to load it like you usually do. I'm going to create an array. My data is input of 0.05, output 0.12, input 0.18, output 22. So this is a relationship, okay? And I'll graph the relationship in a bit. But you can imagine what this is. It's just a bunch of points. So I'm setting up M being input, you know, it's 2 variables. Okay, I called it input. Okay, it's the X and the Y. So really the first column is the input, the second column is the output. And that's what I'm setting here. X being 1s and the input, and then Y is just the second column. Just like I did before in the slide, you know, I said X, I put 1s there in one column. Okay, let me just kind of show what these look like, these variables, after I set them. M is 5, because I got 5 rows. X is the first column with 1s next to it. Y is the second column. Okay, so move on. Okay, now I am in this line right here. I'm going to say A is equal to the inverse dot X transpose dot Y. Okay, the dot product. I'm using the dot product. and that's what was here. X transpose times X, take the inverse, and then multiply by X transpose, and then multiply by Y. 1 second. Why did we not make Y being a two-dimensional matrix? Because Y is only one value. Like here, you can see it's just one column. So it's just a vector. It's just I only have one output. If I had more than one output, or I'm predicting more than one thing, then I would have to make it both regression and classification, I may only have one output. So it's because I only have one output. Why do we have two dimensions in the XOR data set? Y was only one dimension in the XOR data set, our output. Let me just take a quick look because let's go back. Okay. So I'm going to just move this. So when we said what Y was, we only had one output. So we did a feed forward, and we returned A0. A0 had 4 rows. It's a 4x1 because our data set had 4 rows in it. So it was 0, 1, 1, and 0. Okay. Okay, so back to the GitHub. Okay, or to the program, the Python. Okay, so again, this function X transpose X, and then take the inverse, and then X transpose. That's what we got here. X transpose dot X. Okay, we take the inverse of that, we dot with X transpose, and then we dot with Y. So that's how I calculated A. And then I say M is, got to do an as scalar, because I want to convert it to just a number rather than a vector, a one by one vector. I'm going to take M being the second part of A, and B being the first part of A. We go back to the code here. M is the second, B is the first. Okay, and then I calculated the B, or the bias or y-intercept, being this number, 0.08, and the slope being 0.78. Okay, so now let's plot it. And I'm plotting a line, and I'm plotting the points. And the line is what I calculated from, the slope and the intercept. So this is the way you'd plot it, the way you'd show it. So here are those points that I had, and then I just plotted that line with the slope and the intercept. So that's the approximation of those points. So that's basically it. Very simple example. Okay. All right, so now gradient descent. Okay, let's see, got a question. Why do we take 2 dimensions? Okay, why do we take 2 dimensions of the XOR data set? We had 2 inputs in the XOR data set. Here we only had 1 input. This was a little bit of a simpler problem, maybe. Okay, Sachin. All right. Okay, and also Siddhartha, you asked the question only to me, and Imris, you also only gave me the answer. Setosa, versicolor, and virginica. Okay, so okay, the gradient descent algorithm. Let's talk about that. So, starting from scratch again, this is what we're attempting to come up with. Y equals mx plus c. Trying to come up with the m and the c. Right? Now, let's say that we have an m and a c, and let's say it's just some random values, and we calculate what y is based on that m and c and our inputs. And we're off. We're not exactly, we didn't get the right answer because we just randomly picked m and c. If we're off, we can then go and calculate an error. How far were we off? Subtract the actual minus our predicted, square it, add it up for every instance in our data set, every row of our data set, every sample, add it up, and then divide by the number of data points, number of samples. That's our mean squared error. We didn't divide by that, we would just have our sum squared error. Okay, so now that we have that, we have our error, we're going to try to minimize that, right? So let's simplify a little bit. Let's take y hat, because y hat is our predicted. That's what we got when we plugged in the mx plus c, we got a prediction. So plug that in. Now our error looks like this. Okay, now we're going to take the partial derivative of that with respect to m. Okay, so what that means is, okay, partial derivative with respect to m. That means how much did our error change if only m changed? A little bit. If m changed a little bit, how much did our error change? That's partial derivative with respect to m. So that's like taking the derivative. You take the 2, you multiply by the out, you bring that outside, and then you take the derivative of the inside, and all with respect to m. So this is what you come up with. And then you add it all up, and you still divide by n. Okay, that's just a scalar on the outside. Okay, it's just basic derivative math. No need to really understand how we got that, just because you're not going to have to do this in the future. This is just how you did it, how we did it for linear regression. For every type of model, if you're going to use gradient descent, you have to do this derivative. But we're not going to do new types of models. We're just going to use the type of models that are out there. So, you know, if you're even going to look at the partial derivative, because a lot of times you just in scikit-learn you just instantiate it, and you're done. It happens underneath the covers, but you know it's good to see, you know, where that comes from. Okay, so once we do this, we can put back in y hat. Okay, we have this mx plus c still, so I can put y hat back in, you know, our estimated. And bring the 2 to the outside, bring the minus to the outside. We now have minus 2 over n times the sum 0 to n of x, you know, our input, times y minus y hat, which is the error. That is now our partial derivative, okay? So just rewriting it here. Oh, I'm sorry, not rewriting it. That was the partial derivative with respect to m. In other words, how much did our error change if we changed m? And remember, why are we doing that? We talked about this with a neural network. What we want to do is change m a little bit at a time in such a way that our error goes down. And so how much do we change it? We change it with this, whatever this partial derivative is, because that's how much the error would change if we changed m. Okay, so we also need the partial derivative with respect to c. Oh, and I need to apologize. I used c here because my source that I pulled this from used c rather than b. But this is our this is our y-intercept or bias. Okay, I just happen to use c instead of b. If we take the partial derivative with respect to c, I skipped the math part, we end up with just this. But it's very, very similar to the m. In that the only difference is you don't have this x when you take the partial derivative with respect to c. Okay, so now we have a calculation for both partial derivative with respect to m and the partial derivative with respect to c. Now we're going to change a little bit our m and c in the direction of the negative partial derivative. And we're going to multiply by a learning rate, just like we did with the neural network. Just a little bit at a time. We're going to move in a direction of bringing m and c down a little bit. Just not down, but in the direction of the partial derivative. So we know how much m and c, how much the error would change if m and c changed. Okay, so we're going to try to reduce the error by changing m and c a little bit in that direction to decrease error. That's a mouthful, but that's gradient descent in essence. So that same complexity that we have with neural networks, you also have in something as simple as linear regression, as far as the key to neural networks, how they work. It's also the key for linear regression. Unless you're going to solve the linear regression problem with the matrix algebra we just went through. Okay, so now let's bring up the solution of this. Okay, we've got, okay. All right, what I'm going to do at this point, okay, I'm going to stop. And we're already 23 minutes over the hour that I'm setting aside for this. And I'm going to next time pick up here where I left off and do a little bit of review and finish this out. That way, I'll be able to get the quizzes out, get the homework out for all previous lessons, so you can work on that, and also kind of it gives a little bit of continuity between classes. We're not going to just go over the same material that I went over already. This will be a little bit new material because we're going to do this part in Python. But yeah, it'll add some continuity from week to week. I think that will be helpful. It'll give you guys a little more incentive to come to every class, or at least watch the videos before you come to class if you're not able to get that. Yeah, I think it'll be useful to do that, especially right now that we're a couple weeks behind, that I'm a couple weeks behind in getting the quiz and homeworks out to you guys. So, all right. Any questions on what we went over? You guys had some good questions. I know you retracted your question, but it was not a bad question. But yeah, I'll definitely be around for 10 minutes or so, for any questions that you guys have. I'll set up some office hours. They're going to be in the morning. I have to pick the day. Probably it's going to be tomorrow, Tuesdays. Or maybe Wednesday morning. That'll probably work better. How much is linear regression and gradient descent used in real-life ML problems? Okay, that's a very good question. All right, linear regression, if it's a regression problem where you're trying to predict dollars or something like that, I would consider that almost the MVP. Okay, you can actually do more of an MVP where you just set your output to the average, set it to all to 1, set it to a constant. Okay, that would be your real MVP. You'd be off a lot. Your estimation would be way off. But linear regression would be your first step into your MVP. So it's very useful in real life ML problems. A lot of times in your corporate environment, all right, you're going to not need to have a very accurate model. You can get by with just a linear regression. You can get results that are going to save your company money, okay, with linear regression, because you're able to predict something. Whereas before you did any machine learning, you weren't able to predict anything, but you're able to give you have all this data and you're able to pull out some information out of it using something simple as linear regression, something simple as your basic machine learning. So it's very useful in real life ML problems. It's something you can throw together very quick, get results, and you're probably going to be asked to go on to something else very quickly. But you're able to get something out there, and then you get feedback. You may need to add more data in. Well, you don't want to finely tune your models, get to the absolute best model, and then find out you have to start all over again because you have the wrong data set. The data set isn't good enough. You need more data. You can find out how much data you need, with just linear regression. As far as gradient descent goes, that's used in everything. You don't necessarily have to understand how gradient descent was used, but it is the basis. It's that iteratively coming up with an answer. That's gradient descent. There's many forms of it. There's more advanced forms than what I showed. Changing your learning rate instead of it being constant is one example of more advanced gradient descent, but it's still gradient descent. So, very good question. Do deep learning algorithms different than machine learning algorithms? Okay. Machine learning is an overall description of anything that you're using a machine to learn. Where it didn't know something, then it's able to predict after you're done, applying an algorithm. Deep learning is one type of machine learning. It's the one type of machine learning that kicked off it being exciting again back in 2005. We showed that deep learning was able to get better results than other methods, statistical learning or statistical methods. Now, statistical methods are all part of deep learning. Part of machine learning. They're not part of deep learning. They're part of machine learning. That wasn't necessarily the case. You didn't call statistical methods like linear regression machine learning, but you do now. It's kind of a part of the evolution of machine learning. If we have multiple dependent data to get the expected output, what algorithm would be best? Multiple dependent data. So the output, multiple outputs. Which algorithm? Well, it'd have to, we're talking about supervised because we're talking about outputs. We're talking about, it depends on what type of output it is, whether it's classification output or a regression output, a continuous output. That'll determine what type of algorithm. But really having multiple outputs doesn't really determine what type of algorithm to use. Any type of algorithm can be used with multiple outputs. So, trying to think of one that would be better. I think just anything would work to get multiple outputs. What you might end up with is just having two outputs. Two complete models. But yeah, I think all of them would work equally with multiple outputs. Multiple dependent columns would give you the results of expected output columns. Right. Yes. I'm not sure what you're trying to say, but yes, that is, yeah, when you have multiple dependent columns, that means you have multiple outputs. Results of expected out. Yeah, if you have multiple dependent columns, or I think you might be, if you have a classification algorithm that has multiple classes, more than 2 classes, then you would have, you could do it in such a way that you have multiple outputs rather than just one yes or no saying that it's in part of that class. You'd have a yes or no for each class. So that might be where you're going with that. And any machine learning algorithm that's used for classification would work for that. I hope that helped. Get some rest. I know. It's just what it takes. It's awesome. I mean, it's I finally feel like I'm being completely utilized, with teaching these 2 classes. It's a lot of work. Kyle says to get up at 5 every morning, but I'm getting up at 4 every morning, almost every morning. Getting to bed earlier, but getting up early. Doing that 10x rule. Hope you guys listened to that or read it. It's a great book. Very, very motivating. Thank you guys for your questions, for coming to class. Want to see some good homework. Oh, got a question on Q&A. All right. As we redefine the output of a model multiple times, what are the pointers we can use to identify that we have reached a good level of maturity and the model may not be or need to be refined further? Okay. As we're training, when we've converged, really, when we're not getting, I mean, there's a couple of things, and we will get into that. All I did tonight was show the training, but what we can do is do some validation or testing, depending on your vernacular, to see whether your test set is becoming more accurate. If your test or validation is not getting any more accurate, if it's getting worse as you train, as your training becomes better, then you're going to, then you're overtraining. And you should stop and or back up. No, you just stop. Don't train any further if you're starting to overtrain. You'll need to change your model if you still want to become more accurate, but you don't want to continue training. You don't want to overtrain because you're predicting worse. Your goal is to predict better. So that's one place to stop.